Welcome, everybody, again to Ham Radio Perspectives. I'm Quin, K8QS.
And I'm Tom, WA9TDD.
And, of course, what we're doing here is very strange today, very, very strange. We are going to jump in where a lot of people get into deep trouble here, and that is end-fed antennas. If you look around on the internet, as I'm sure you have, both of us, or you talk to hams, there are people who praise end-fed antennas, and there are people who hate end-fed antennas. And in fact, there are a lot of people out there that say they don't work. It's all a hoax and so on. So we're going to go through that because we have both used them of various kinds, horizontal and vertical, and we have had a lot of luck with them. But we thought what we would do is share with you some of the secrets behind how they work and using them well. And so be prepared after you watch this once to go back through it and write down some of the comments that we make and some of the information. We're doing this as a PowerPoint so that we have a version that we can share. And if you want to get a copy of this, all you have to do is send me an email. I'm Quin, K8QS, Quebec Sierra. Go to QRZ, get my email, send me a note and say, hey, I'd like that PowerPoint. In fact, we have a PowerPoint version that has more slides than this, but we didn't want to make this too long. So sorry about that long interruption, or introduction, but that's kind of where we're going with this right now. Success for end-feds. All right. I think, Tom, the confusion, most of the confusion is caused by the fact that there are two types, basic types of end-fed antennas. Do you agree with that?
You're right. The two types. There's the half-wave end-fed antenna, and that's abbreviated HWEF. And most of those are commercially made. They could be either non-resonant or random length end-feds, but most of them are homebrew. And they're different enough that you have to understand how each one works.
Right. You can use either one successfully, but they work very differently. Okay, so let's get into this a bit. The overall advantages of end-fed antennas, the two kinds, the half-wave and what often is called the non-resident or random. Again, that half-wave is a half-wave long as an end-fed, and the other one has to be a random length. We'll talk more about that later. But what are some of the advantages, Tom?
Well, they're cheap to make. I mean, you can roll your own from basic parts, and they're also lightweight, which is advantage for going on, parts on the air, summits on the air, whatever on the air, or simply as a backup antenna for your home installation.
Yeah, or if you're in an HOA area and you want to be able to go out at night and throw an antenna up in the tree and then take it down when you're done operating, it's easy to do.
Yeah.
And homebrew parts, you can homebrew these. You can buy some parts from other people. So, and we're talking about really lightweight. Okay, so the ones that are made for QRP use for the parks on the air and all are just incredible. You toss them in a little bag, it's like a lunchbox, and bam, you're out and going. Now, multi-band is another advantage, but you have to be careful here, because when we say multi-band, we don't mean that it is automatically in every case going to work on every HF band that you want it to. And you have to be especially careful with the half-wave one, because when you're going for half-wave, you're going to be operating it on multiple harmonics, if you will.
Right.
And so you have to get that first measurement right on the lowest band. It's a bit easier, actually, to go multi-band with a random one that is cut so it doesn't work exactly on any one band, and then you use your tuner. There's also easy deployment of these things. So, as I say, you can set them up right away, throw a wire out. We'll talk about that. My experience has been, Tom, that with the half-wave end-fed, and I researched this online, they generally tend to work better if they're more horizontal. So you will go online and find all kinds of people who will throw something up way up in a tree on the far end. They're feeding it down below by off the ground or by their deck or something. And then they're doing what's called a V, and then the antenna comes up and comes down a ways. And I have not had as much success with that. I find that I have to do a lot of monkey business with the wire to get those to work well. Whereas when I cut it for a half wave and I go out more or less horizontal, even if it's not high in the air, and I've had an 80-meter half wave out back here, maybe 15 feet in the air, that worked really well. So again, that's my experience. Of course, they're very stealthy antennas.
Right.
So when I was in the dorm at the University of Illinois, I had one, and I just threw the wire out the dorm room window. And I can't remember that type of wire, Tom, but it's extremely thin, and I think it's used on coils and stuff, but you can hardly see it. And so I got some of that at a hamfest, and I threw it out, climbed the tree, put the end out there, and that's what I used. I talked to an ambassador who's worked with end-fed antennas around the world in situations in the compounds that they were in countries where they didn't particularly want the ambassadors working HF radio, but he would use them. And of course, a lot of people use them in HOAs too. What are some of the other advantages, Tom?
Well, they're fun. They're fun to tweak and play with, and every little change affects everything else. And I find that the non-resident end-feds are the most interesting because they take the most fooling around with to get them to work. As you mentioned, the half-wave end-feds, you can only operate those on the first, third, and fifth harmonic successfully. With those that are cut non-resident for any particular frequency. I mean, I've got one now that's run at 53 feet that I think is resonant on like 8 megahertz. But running it through a tuner, I can tune anything from 40 meters down through 10 meters pretty successfully. Not going to get a flat 1.5 to 1 SWR on any particular band, but it'll be easily workable without blowing up my radio. And they're good for receiving a strong signal on an end-fed antenna, which is one of the critical aspects of an end-fed antenna. They're fairly less noisy than either a dipole or a vertical antenna.
They can be.
They can be.
Mm-hmm.
It depends a lot on your. Well, we'll get into later the counterpoise and the radial field that you might have attached to that antenna.
Right, and an un or some type of transformer that you have in the line too can cut down on the noise that you're picking up. What I really like about when I'm on an end-fed, Tom, is I'll work some guy, nice ham, and he's got dipoles up at 80 feet, and he's just having a ball working the world and all. And I say, yeah, well, I'm running a 7300 here at about 40 watts, and my antenna is an end-fed at 30 feet. And, and then it turned over to him, and there's dead silence. And you know what he's thinking? This stupid operator. How can he possibly think that he's getting out on an end-fed? Meanwhile, he's already given me a 5.9 plus 10. So I love it when skeptics of end-fed antennas give me good signal reports on an end-fed, and then afterward I tell them I'm on an end-fed. So, okay, so these are some of the advantages. Now let's get into some of the disadvantages. I know the text here is fairly small, so if your screen can't get into this too well, send me an email and I'll send you the PowerPoint. What are some disadvantages, Tom?
Well, like any antenna, you need some knowledge about building and deploying even the commercial-made antennas. You got to decipher between the confusion regarding the half-wave versus the non-resonant designs, and get yourself ready for some exciting decision-making on that end. you need a counterpoise that could be generally essential for end fed half wave end fed, and it's a very important for a non-resonant end fed.
Yeah, the counterpoise we'll get into and show you some examples of that. But basically, a counterpoise means the other side of the antenna because it's an
Right.
end fed. And when you think of a dipole, okay, you got the two parts. With an end fed, you've got the one side of the quote unquote dipole. The other side becomes the counterpoise, and there are different ways that people work this out. Some that work better than others that we'll talk about. Another disadvantage, and this is wild. This is one of the things I love about ham radio, Tom. Every installation of an end fed results in different measurements and performance.
Mm-hmm.
So you cut this thing, you get it out there, resident, non-resident, and you put it up, and you see what starts to happen. And you test it out. You get the SWR, put the antenna analyzer on it if you have one, and suddenly you realize that if you start moving where those wires are, or changing the length of the main feeding wire or the counterpoise, things start changing. Or if you go out in a V, up and then down, it's different than if it's going out horizontal. So one of the reasons we think that end feds get a lot of negative publicity is that somebody goes and tries one and they think, this thing doesn't work, but they don't try a different kind of installation at their own place. So that's our take on it.
Right. And you get, the unpredictable performance, get all kinds of funky radiation lobes and directivity going on. And depending on the construction and installation, get directions changing, even band to band. And that's the one nice thing about them is they are unpredictable.
Yeah, so if you put a dipole up, people will say, well, on the side of the dipole, broadband is, that's where you're getting your power out and you're receiving the best. Okay, so if you get an end fed up there and assume that, you're going to learn real quickly it doesn't work that way. I mean, when these things get modeled, they show all kinds of weird things. It's like Rod Serling or something out there in the Twilight Zone. And so what works in one direction really well on one band may not work in that direction on another band. And so we often call these shadow directionalities. In other words, you don't know they're there, and suddenly you can't hear a station. And it's just not there, but your neighbor down the street can hear it fine, and you're in a QSO, and this other guy breaks in and say, what the heck is going on? You got a lull right there. So there's unpredictable performance. And if you don't mind that, and if you can live with the excitement, this disadvantage is not so bad. Now, of course, possible danger for these antennas, and this we'll spend some time on here, is for this common mode current. We're talking about RF current. So you've got voltage and you've got current in RF, and impedance is the ratio of voltage to current. But let's just say when your signal goes out to that antenna, very likely with an end fed, you're going to have some of the current, which we call common mode, coming back down to your station, and it's coming back down on the outside of the shield of the coax. Okay. I know this is going to sound crazy to some of you, but you're using coax, regular coax with a end fed. You've really got like three lines going on there. Okay. You've got the center connector in the coax, and then you've got RF that's on the inside of the shield and on the outside of the shield. And this outside of the shield is this common mode current that comes back at you because there's not a perfect tune to the impedance of the antenna. And so this is where you get this going back, coming down in the feed line in the home, in the shack, and I've got my lights here in the living room next to me, and they're coming on and off. And my wife says, what the heck are you doing there? Why are the lights coming on and off? Call the electric company. I say, no, it's just me. I'm trying to get my end fed working properly. Now this can be dangerous because, you can get what we call bit on a metal mic if you get your lip too close to it with that RF common mode current coming down. And but there's an advantage here, Tom, that people don't talk about much. In fact, we haven't seen a video on this yet, but I think it would be possible to make pancakes on the top of your rig if you've really got bad common mode coming down there, man. If you don't blow up the rig, at least make some pancakes while it's still hot. What other disadvantages can you think of, Tom?
Well, because of the CMC, the common mode current coming back down on the coax, it's best to use as low as power as necessary. Especially in a QRP situation, they work fine. I wouldn't run over 100 watts into an end-fed antenna. You could get a balun and on the transformer to change the impedance and the amount of common mode current coming back in, but those are going to heat up the core, and you'll end up destroying your balun. So, to me, that would be one advantage. I run a lot of digital. I rarely run more than 40 watts into the antenna, and everything works out fine. But I'd be very careful about trying to go QRO with an end-fed antenna.
People do it, and there are commercial unbalanced transformers out there up to, I found one time up to 5,000 watts, they claim. Now, why you would need 5,000 watts, I don't know. But I always assume whatever the rating is of the I'm going to be well below it. So if it's rated at 100 watts, I'm not going to run it close to 100 watts. I might run it at 80 on CW, but on the digital modes or on CW or certainly on AM or FM, you don't want to be anywhere near 100 if it's rated for 100. That's my take on it, for good or for bad. Another disadvantage that people don't talk about, but it's significant with NFEDs, is the noise that you can get. We mentioned earlier, these antennas do not have to be super noisy, but they can be noisy both from the noise that's generated in your feed line, that coax you've got going up there can generate noise, the noise associated with that common mode that's out there. And then it's picking up noise from all the stuff in the neighborhood, all the LEDs and the crummy little wall warts and everything else that are being picked up. They tend to pick up a lot of noise of various kinds. And so people do manufacture, but you can build your own too, uns that are especially good to run right where the coax comes into your rig or into your amplifier. And these are basically noise reduction uns. And I did a little bit of testing yesterday with my other antennas just to see how much noise I was getting on them, comparatively speaking. And it was quite a bit. So I thought, what the heck? So I ordered from Palomar one of these noise suppression units. They're not expensive. And later we'll do a video on it if it works well. I didn't ask them to send me one to test it. I just plain bought it. And we'll see. And Tom, you pick up the last disadvantage.
Well, the last disadvantage is there's a lot of negative PR about end-fed antennas. The nattering nabobs of negativity out there, to quote Spiro Agnew. Some say they work and they swear by them. Some say, well, that's not an antenna. I had a new radio 10, 12 years ago that I was running through an end-fed through a tuner on the radio. I had checked the antenna with my antenna analyzer. It was perfect on the band. Everything looked good. Reactance was great. And I blew out the automatic tuner section, or I blew out the antenna tuner section. I sent it back to the factory. It was still under warranty. I get a call. They asked me, well, what kind of antenna are you using? I told them, well, I'm using an end-fed antenna. I described the antenna and they said, well, get a real antenna.
Oh, they said
That's
that to
your problem. Huh?
He said that to you?
Oh, yeah. He said, flat out said, you'll get a real antenna.
Oh, boy.
And I've been using end-fed antennas probably longer than this guy's been in business. So, yeah, you're going to get a lot of, I can't hear you. What kind of crappy antenna you're running?
Oh man.
Um, that's not a technical disadvantage of the antenna, but one that you're likely to hear if you're describing your antenna.
Yeah. Okay. So again, what we're doing with this video is helping you through this, so you do the best you can and know how these things work and deploy one or more that work well. So let's get into the really interesting aspects of this. Here's a slide, and we've put on this slide the history of the NFED is a major part of the history of HF radio, period. Stop. I mean, NFEDs have been out there since the beginning, used very successfully by people that know how to use them and those that don't. So you see two little drawings here. Let me put this just on slide alone, give you a little bit bigger picture. The one on the top is the old-fashioned driven NFED. You see any length going up there. It's a random length or non-resident, comes to the transmitter, and of course you've got a little bit of a ground too. So that's the antenna. That's it. It's driven with the pi network in the older vacuum tube transmitter. So Tom and I had older rigs with I won't say antenna tuners built in, but a pi network that you would use to tune for a specific frequency.
Right.
Like a built-in antenna tuner, but more robust than the antenna tuners that are built into rigs today. And so it was assumed that you could take any wire and throw it out there, maybe have to adjust the length a little bit, and you'd go ahead and try to tune that sucker, and you would probably have some common mode coming in. You'd get bit on the lip and so on. But that's a big part of the history of ham radio. And then you look on the bottom, and now all we've done here is added, this is from the ARRL antenna book, we've added here the diagram for an antenna tuner, an L network that can be used with a modern solid state transmitter, of course, built into a lot of rigs nowadays. They're not as robust a tuner. And so things will happen like happened with Tom with his poor thing. I think that was a Kenwood that you blew up and sent in.
Yep.
And the antenna tuner couldn't really handle whatever level of common mode was coming in. So when you look at these two right here, you see a lot of the history of ham radio as it's represented in the use of the NFED. Now, we're looking at these, and they're up there. They've got a little bit of a vertical angle to them. But let's just make it more fun, Tom, and say that one thing to keep in mind is voila.
The 40-meter NFED vertical antenna, which is essentially, it's an NFED antenna, only oriented vertically. And this is what I use most of the time at my home radio station. The biggest difference here, other than the fact that it's vertical rather than horizontal, is I have a counterpoise, a radial field underneath the base of the antenna. And this is common. Any vertical antenna is basically an NFED antenna, that if it properly works. And what makes it work is that radial field or counterpoise underneath the antenna. It provides the low reactance path to ground. It does eliminate a lot of the common mode, and other than the radiation pattern, which is how they say radiates poorly in all directions, Quin.
Yeah.
It's a great antenna. It tunes up fine, but I think, in my opinion, the secret to that is a large radial field underneath the base of antenna. In my case, I've got 16 counterpoises underneath the base of antenna that are buried about an inch below the soil line.
And those are different lengths, right?
Right. Actually, they're pretty much random lengths.
Okay.
I got some wire, and I just chopped it into 33 feet, anywhere from 33 feet to 14 feet lengths. and spaced them around the base of the antenna like a cartwheel spoke.
Mm-hmm. Now you can take this antenna, vertical and fed, let's just call it a vertical, and you can move it up in the air. We know from some of the reach that if you can get it higher, it might work better. But the problem there is, well, what do you do for the counterpoises, the different wires that you want down below that represent the other quote unquote half of this vertical dipole? And of course, it gets pretty problematic to have a lot of those up there. So what Tom has got is a tremendous ground system with this. Tom, I'll tell you a quick story. I don't know if I've ever told this to you before or not, but when I was at the University of Illinois, we had 250-foot towers that used to be used for AM broadcasting, and they were on either side of a practice football field. And so one day I got the idea. I said, hey, 150-foot tower, I could use that as a quarter wave on 80 meters. So we actually figured out how to load that sucker up, and it had a tremendous ground system underneath the whole football field there. And so we got the right spot to feed it up a ways on the antenna. I think we initially used the clamps that you would use if you're boosting a car, the battery's dead, and we figured this out. I would get on 80 meters at night working DX with that sucker, and 2,000 watts or whatever the power limit was. And I'm telling you, Tom, boy, with that ground system, did that work. Yep. Holy cow. So here, let's go on a little bit more here. Now we get a bit more complicated. We don't want to throw you off too much, but take a quick look at this, gang. I'm going to go on full screen with it again, just so you can see. Here's your typical end-fed antenna system. This is from a Palomar, and Palomar, I told you I just ordered a noise reduction thing from them. They make a lot of good stuff for different kinds of antennas. Quality outfit, quality engineering, quality manufacturing. They don't pay us, okay? I'm just telling you that. You can depend on them, and they give you good information on the phone, too. So here we have what's typical, a 49-to-1 transformer, or unbalanced to unbalanced for half wave, or a 9-to-1 transformer for random length. So these are the most common transformers or uns that are used to convert from one level of impedance to another. So our coax is 50. Whatever the antenna is, we want to get it as close to 50 as we can and then tune it up. So on the left side, you see the antenna, and then it comes down to Z, and there you see the impedance transformer, or un. And then below that, you'll notice those three little lines, the counterpoise system. Okay, some people would say, well, those are ground radials. Well, let's just call them counterpoise system. When you think of ground radials, you might think they have to be on the ground, or you have to have a ground rod or something like that, and you don't. So, and then you've got the coax. The coax is that black line that's going from Z, the impedance transformer, to the right to FC, which is the feed line choke. We'll talk about that choke in just a minute. So the purpose of putting that blue line directionality from the Z, the transformer on the left, to the feed line choke on the right is to show you that that's where the common mode current returns down the outside of the coax back to the transmitter. So you got, in theory, from the rig on the far right, your signal, your RF goes to the left along the coax to the Z, up to that antenna and out, and all is well. But in truth, you're going to have some of it coming back represented in that blue arrow going to the right. And so you get what we often call a common mode choke, to choke out that current. It's current that's coming back, RF current, called common mode. And there are different ways to do that. You can do it yourself by getting a little ferrite, piece of ferrite, what do you call it? Not loop, but...
a ferrite, yeah. Donut.
A donut,
It's
a
a
ferrite
donut.
donut.
Yeah.
And then usually you'd say like a 41 mix, and then you would wrap the coax through that. That will do a fairly good job if your situation is not too bad with the common mode. But if you need more, you can buy a commercial deal, and then you have your rig, and of course your rig is grounded separately, and that the purpose of that rig grounding is not primarily to deal with the common mode. You want to try to get rid of the common mode before it gets to your rig. Okay, so this right here is a typical NFED antenna system. All right?
Right. Right.
All right. So anything you want to add on this before we go to the next slide, Tom?
No, I think you pretty much covered it. It gets starts to get more confusing as we go on.
Yeah. Okay. We put this one in here, Tom. Why did we put this in there? I'm trying to remember now. Oh, to show how the coax connects.
Right. This is an illustration of what happens with the coax and the common mode current. You notice the center of the coax going out to the antenna. But however, on the shield, as Quinn had mentioned earlier, it's actually a double conductor. The inner part of the shield carries your RF current out to your counterpoise. However, the outside of that shield also acts as an individual wire that carries your common mode back to your radio. So basically, this is an illustration showing how it's three wires actually out of a two-wire coax. So what you want to do is you want to eliminate that common mode current coming back into your shack, which is carried by the outer part of the coax shield. I'm not sure if it's inner or outer part to be exactly, but it's called the skin effect. And because the braid is flat, it essentially mimics two conductors.
Right.
One end comes out, one end comes back. So that's where you want to choke off the common mode before it gets back into your shack and causes all kinds of problems.
Yeah, we took this from VU2 NSB. You can see his website address there too if you want to go in. He's got some great material on that website, including some of the drawings of what happens with an NFED in terms of its directionality and all. So what I like about this, Tom, is it shows like a dipole. And so that side on the red, on the right, that's red there, where the center of the coax is coming in, that's going out on that half wavelength on one side that you've got for a cut for a half wavelength on whatever band you're on. And then they've got that other side on the left called the counterpoise. And so what gets interesting here is you start fooling around with different lengths of this counterpoise and different orientations, and it affects how well the antenna works, and it also will increase or decrease the common mode current coming back down that outside of the braid of the coax. So it's quite fascinating. And there's a little mention here of Kirchhoff's law, which you can look up, which means basically you want to try to get these two sides as equal as possible in impedance. So otherwise you're going to have that common mode coming down. That's a simplistic view of it, but that's basically it. So look at this, gang. This is interesting here. We have an MFJ antenna tuner, and we just wanted to show you this because this is less and less likely to be anything you find on any antenna tuners made. You see all of those coax connectors on there for coax 1, coax 2, transmitter, external dummy load, and all those are the 4 SO239s. Well, in the old antenna tuners, you didn't have any of those. None. All you would have would be what those little red connectors are on the right. So for a balanced line, like if you're using a window line or something like that, where you have two wires going up to the antenna, you'd use those two connectors on the top. And then you see the one connector on the bottom that just says wire and the other one that says ground, okay? So you start you jam that wire into the one that says wire, and you put a hole in your wall of your house, and you run it out there. There's your end-fed antenna. And then if you want to try to fool around with a counterpoise at that point, you can do it with that ground. But generally, that's not where you're going to do it, as we'll explain. But we wanted to show you that so you understand part of what's going on. What's this, Tom?
Okay, this is a Valen or possibly an unknown. This one looks like a one-to-one winding to me, so that would make it an unknown. And basically, what it is you have your lead coming in and the one going out, and it's wrapped around a ferrite coil, each the input and the output. And basically, what that does is it sets up canceling magnetic fields, to put it simply, that hopefully eliminates all of or most of your common mode currents. But that's
Right.
basically what it looks like on the inside of those magic boxes that you put in line to eliminate your common mode.
Yeah, and some of the manufacturers, if you don't make it yourself, if you buy one, they will have better quality wire. They will have better quality ferrite there and other things. So, but again, on EHAM, you can look up reviews, or you can call any of the major companies that sell this kind of stuff to find out which one to get. We gave you the figures earlier on the ratio of impedance. This, as Tom said, being a 1-to-1. It's basically just designed to get rid of some of that common mode, which is really important to do. We go back one here. Okay, so this is another way to look at the end-fed half wave thanks to PA9X. And so there you see on the top part of this chart, 1/2 wavelength. This is for an end-fed half wavelength. You see the antenna in blue coming down into the 49-to-1 impedance transformer or matcher. And we just put down there, well, what is the impedance like on an end-fed half wave? Well, depending on it, it's probably going to be between 2,500 and 5,000 ohms of impedance.
Mm-hmm. Right.
So you got your rig and your coax, and you're thinking about 50 ohms, and here you got 2,500 to 5,000. So you put that 49-to-1 in there, and bam, it reduces that impedance to somewhere close to 50. And then you have your little bit of coax you see on the top drawing there, 2 meters to 4 meters of coax. And then it goes into a common mode choke, just to choke out any common mode coming in. And then the coax feed line that goes to your rig. So that's what it looks like. Now, that one of the tricks here on the end-fed half wave in particular is to make that distance of coax between the 49-to-1 impedance transformer and the common mode choke as short as possible. I have actually just sometimes used one of those little connectors, not even any coax, just to put the two right next to each other. So example number 2 is likely to help you out a little bit more. And you still want to keep the distance between the common mode choke and your rig as short as possible as well. So try to keep the distances short all through here from the end of the antenna there at the 49-to-1. You see that down below in the example down below. Now, Tom, you tracked down this thing. What the heck are we going to see here when I play this video?
Okay, this is a video of basically the harmonic 40-meter band antenna, and I believe this is the second harmonic. But the video is going to show how the waveform varies in the antenna on multiples of the fundamental frequency. So what can I say? Roll it.
Okay, I'm going to roll it, and keep your eyes going here, see it through, and you may want to go back, guys, and replay it another time too if it helps. Whoops, that didn't play, but I am going to get it to play. Hold on here. Okay, I played that through twice, Tom, just to so people could follow through. So we're dealing with the end-fed half wave. We're dealing with these harmonics or multiples, and so I mentioned to you before, Tom, not on a video, that when I put up an end-fed half wave for 80 meters and above in frequencies, I found that I had to cut the end fed so it would work best on the lower end of 80 meters,
Right.
the lower end of the sidebands part. If I cut it to include the whole band up on the right side, the harmonics were too far off for me to be able to use the antenna tuner in the rig. So you're always cutting. The critical first cut on an end fed half wave is for that first band, to get that right, that it'll work on others. Try it out with an antenna tuner and see what you can come up with. But it's amazing when this works well. It's a great antenna.
So,
all right, here we go again. And I'm trying to get past this sucker, so let's keep going. Okay, so here we're going to kind of conclude things a little bit with some of the design essentials that we've mentioned that you should keep in mind here as you work on these antennas or decide to buy one and you say, yeah, what should I be looking for and the like in these. So these are design essentials for the end-fed half wave with a 49-to-1 transformer, okay, or un. The antenna wire should be cut for a half wave based on a frequency in the middle of the lowest band to be used. Okay, now again, as I said, for me on 80 meters, it's big, broad band. I had to bring it down lower, but that's typically the rule for it. Second would be the counterpoise should be, now this is so important, Tom, let's talk about it, should be about 0.05 wavelength of the lowest band.
right.
So for 80 meters, this would be approximately 12.5 feet. So people will say to me, Tom, when they're, especially new hams in the area, they're putting up these end feds, and they figure that the longer the counterpoise, the better. So they've got an antenna, you know, that's, let's say for 15 meters, and they're going to run 100 feet of counterpoise out there,
Wow.
thinking, boy, this is really going to do it. And they don't quite understand that. You want that counterpoise to be able to match in these different multiples or harmonics. Anything else you want to say about that one, Tom?
No, I find that this holds true if you're using a single counterpoise, as I described in my radial field under my vertical for multi-band operation. I found that if I run a random length, starting with the a half wave at the lowest frequency band, and then cutting random lengths anywhere between, in my instance, about 33 feet down to about 14 feet, and put them in a radial pattern underneath. It gives me multiple band coverage. So for a single counterpoise, I believe this formula is correct.
Correct. And that's what we're looking at here. Now, you could say more the merrier for counterpoises, especially if it's a vertical on the ground. Get out there as much as you can. One thing I should mention here, Tom, I don't know if you've seen these or not, but there are some end-fed half waves out there that are manufactured, sold commercially, where what they do, there's no counterpoise. And they say you don't need a counterpoise. But what they're actually doing is putting a choke down the coax at the point that is here, about 12.5 feet. So by putting a choke there, they're trying to get that outside part of the coax, the outside of the shield, to act like the counterpoise within the coax itself. Okay, and so they sell you the whole package. And you might not know that that's why they say it doesn't need a counterpoise. They're trying to use it. I have no idea how well those work. I haven't tried them. It's a concept anyway. Number 3 here, when a wire counterpoise is used, a choke balun is best placed, we showed you this, right behind the 49-to-1 transformer. And then number 4, in lieu of a wire counterpoint, you can allow the coax shield to act as one. Oh boy, here we go. When used in this manner, the choke should be inserted in the feed line at a distance from the transformer equal to the calculated counterpoise length of 12.5, as I mentioned with some of the commercial models. This portion of the feed line must also be up off the ground and can be in any orientation, but should not run under the antenna wire. So if you want to try that, you can give it a whirl. Let's give one more design essential here, Tom. Go ahead.
Well, if your feed line is above ground and runs under or parallel to your antenna wire, you need another 1-to-1 balun in the feed line before it enters your operating position. Your feed line is going to act like an element essentially of your antenna. So what you want to do is you're going to eliminate any chance of getting any common mode current or re-radiation coming back into your shack from the coax. It's supposed to run your coax at a 90-degree angle to the direction of your antenna.
Yeah, Tom, these 5 design essentials we got from Balun Designs, we wanted to give them a shout out as well. I bought a bunch of products from them over the years. In fact, I have had them make a couple of baluns to my specifications on occasions for specific situations I had. So they're a good outfit as well. Balun Designs is where we got these now. So we've been talking here about design essentials for end-fed half wave. Now let's look at the non-resonant ones that we looked at or talked about earlier, the random length non-resonant end-feds. Here, the whole trick is to create a length of antenna that is not naturally resonant on any of the bands that you're going to use it on. Okay, so that's why we began this presentation saying think about end-feds as 2 different kinds. The end-fed half wave, where you're working it on multiples of that initial half wave that you cut it for, and then the other one is random length. And so here you have from Palomar their suggested random lengths. And you could look at this. What bands do you want to cover? And then the wire length in feet and the minimum coax length in feet for them. So this is a simple chart you can use if you want to try the random length. And I think you should, gang. I think you don't listen to those nattering nabobs of negativism. As we said earlier, these random length end-fed antennas are part of the history of HF ham radio, been used successfully for years and years and are still used successfully. You just got to know what you're doing. Anything else you want to add about the non-resonance here, Tom?
Yeah, the most important thing about a non-resident end-fed, and you can look up the table similar to the one you see here. There's some lengths you absolutely want to avoid because they're going to be out of the range of any band that you're going to be able to use, and it's going to be out of the range of any balun choke to prevent any kind of common mode coming back at you. So you can play with variations between those 2 non-used points. I find that 53 feet works well for me for 40 meters, 20, 15, and 10. Doesn't work well for 12 meters or 17 meters on the work band. So depending on what band you primarily want to operate on with the antenna, play around with it. Your configuration shape, whether it's an inverted L, a flat top, sloper, zigzag, makes a difference in how the antenna operates. The length of counterpoise, the coax feed length makes a difference. Feed line chokes, noise, filter placement goes at the radio end. whether you feed it at the top, the bar, the bottom, or you feed a sloper at the top end, your soil conductivity, length and number of counterpoises. Boy, these NFEDs, they throw everything into the mix in order to make a successful antenna. So
That's why they're fun. That's why they're fun.
Why they're fun, because let's face it, most hams, once they've purchased their equipment, let's face it, are they appliance operators? Where can you have the most fun building stuff without spending big bucks other than your antenna? And an NFED antenna, whether it's resident or non-resident, gives you a lot of fun factor to play with. And you discover things that you never knew before.
Right. And just to emphasize what Tom said, note on those wire links there that they give you ranges, which means, as Tom said, there are areas there that you don't want to use if it's not in those ranges. Okay. And you can go online and find all kinds of people claiming that a particular length is the best one to use that will get you on every band under the sun. I have not tried one of those to see if that's true, but I'm skeptical. There's a little more complexity than that. So take the bands that you're most likely to use and design it for that. Now, NFED SWR factors really quickly. This is from Palomar as well. The configuration shape, okay, inverted L, flat top, sloper, zigzag, all of that's going to change. What else is going to change?
Well, your counterpoise, your feed line, the choke placement, your noise filter placement, whether it's fed at the top or the bottom, the soil conductivity, length and number of counterpoises, radials, whatever you want to call them. What are the lengths? How many do you have? Are they multiples of quarter wavelengths, or should they not be multiples of quarter wavelengths? That's about it. You know, what else can go wrong?
Well, our yard occasionally floods, and I mean it, the backyard really floods, even to the point we get mallard ducks showing up in the spring, thinking that they're going to be there all year. Eventually it dries up. But one spring I thought to myself, this is too good to be true. So I quickly built my little 10-meter NFED, and I threw it out right over the pond in the back because I wanted to see how well it would work over water. And it was great. Not as good as salt water, but hey, you know, not everything is going to work extremely well. So, you know, we really want to thank you for tuning in. This has been a long video, but Tom and I, as you can tell, love NFED antennas because of their unpredictability, but also because when you hit it right in your location with one of these suckers and you're working on it yourself, there's great satisfaction and enjoyment with them. And you can feel in your bones, gee, this sounds crazy, Tom, that you're part of the history of HF radio. All these guys running around out there in fields with different link wires, you know, and their big old transmitters, trying to tune these things up. And you're part of that now in a different age. So thanks for watching. Please subscribe. It's Ham Radio Perspectives. There's a little bell button up there you can hit. You'll get a ding whenever we post a new video. And down below, you can subscribe. Give us a thumbs up. You know, we like it when we get thumbs up. It keeps us going. It shows us that we're not just making complete fools of ourselves, only partial fools, depending on how many thumbs down we get. And we're grateful for you for tuning in. And if you have any comments about NFEDs or whatever, put them down below. We'll try to keep up to it. We try to answer within a day or two every comment on all of our videos, except when we had a time last year, we put some videos out that had so many views. I mean, you're talking beyond what we could keep up with. So we just had to give up. But give that a try. And also remember to send me an email at I'm Quin, K8QS, Quebec Sierra on QRZ if you want the whole PowerPoint. And I'll send that off to you. So, Tom, you take it away.
Okay. That's a long video. I'm sure we're going to get comments pro and con.
Yeah.
So we're buckled up and prepared. And What else do you want to know about NFEDs? Ask him.
Yeah, I'm glad you pointed the opposite direction. I'll
Well,
point to you.
that guy over there.
All
I'm
right.
Tom, WA9TDD.
We'll see y'all later, gang. Thanks.